Hello, it's I, Paul. Let's get into it. So the goal is we're going to find the mass of the black hole, and then we're going to find the initial velocity for a spaceship to fly close to the black hole and then escape the system. Alright, so we're going to use these formulas: Newton's second law, velocity update, as well as displacement update, because we have a force that is non-constant. There's going to be acceleration, there's going to be velocity, so therefore there will be displacement. Bang. Alright, now we got some parallel and perpendicular stuff, because orbits are like the circular motion, right? So we're going to be using the parallel components, which is the magnitude of the velocity and the direction of motion. The perpendicular component, which is the direction of the velocity and is pointing towards the center of the kissing circle of that circular motion. We've also got the gravitational force, because this is acting in space between objects. The force of gravity is negative GMM over r squared times r hat. R squared is the magnitude of the position vector, m's are the masses, and r hat is the unit vector. We've got some free body diagrams. In the first block of code, there is black hole and star. They're acting gravity on each other, and then you add the spaceship, so everything has a gravitational pull acting on it, basically. Pretty simple stuff. Alright, the initial conditions, right? We got to define the gravitational constant, the mass of the star, the delta, and the initial time. We're going to start time at 0, because we want to go from 0 to whenever the simulation is over. Just makes it easier. Delta is 1, and we're going to do star. The mass of the star is going to be 1 to make everything easy. We're also going to use this. dp/dt, as you'll see in the next slide, is defined to calculate the F net, and then this is calculating our p hat here. So these are some of those that parallel component that's important. And this is the iteration large bit of code. Basically, we're taking those initial conditions, we're calculating some stuff from them, like the final velocity, the final momentum, and the net force. And we're going to use all of that in combination with the parallel force that we find and the perpendicular force that we find to update the position and the velocity of our model. And when all of that is put together, we get this. Wow. This is so cool, guys. Lit. So as you can see, yeah, I went in a elliptical orbit, right? And this elliptical orbit is going to cause the gravitational force to be less the star is far away from the black hole, and greater the closer you are to the black hole. So the closer to the star, the greater the force, the faster the speed. And we have to discuss error. I mean, it's a computational model. There's not really going to be all that much error, but it could have resulted from some rounding errors by the script. Alright, this is our second model with the spaceship, right? So as you can see, exact same like definitions and stuff. You know how it is. We took the bh.m from the first part of the lab, so that gives the mass of the black hole that we calculated. And then we're going to take everything, and it's basically the exact same equations as you can see here, except now we are calculating backwards to the initial velocity of the ship so that it can escape, right? And so escape velocity is going to be when, like if you're looking at an energy graph, it's when the kinetic plus the potential is going to be 0, right? So we want to get that escape velocity, which we're calculating here using basically the same equations we used before in a different format, including the ship, right? So bang. This is how we're going to update the planet's velocity and the planet's position, as well as the ship's velocity and the ship's position. That's how we model the escape. Here is our part 2 discussion. So initial velocity is that number, that vector. You're going to get shot out of the black hole system, and errors could have resulted from the rounding errors and the truncated gravitational constant. What does it mean? Right, so some information about this, right? The net force can also be seen as the change in velocity over the time, right? Because it's acceleration. It can also be seen as the sum of the change in velocity and change in time in both parallel and perpendicular components, which is good to know because if you're working in parallel and perpendicular, right, you can then find net force, you can then find velocity and displacement. Bang.